Okay, so moving into the next topic here, radioactive decay, okay, and radiation. Now, what is radiation? Well, it's kind of a catch-all term. You've seen radiation, right? Radiation is essentially anything that moves and carries energy. So it was observed that some naturally occurring materials emit or radiate high energy stuff. I say stuff because it wasn't actually known what it was at the time. So it was first noticed by a guy named Henry Becquerel when a sample of uranium he had in a dark drawer where no light was getting in there was causing little specks on a photographic plate to kind of fog up, right? Just like that photographic plate would if it were exposed to light. If you've ever taken something like a Polaroid picture, it's the same idea, okay? But it was in a dark drawer where there was no light. So why was this happening? Well, it was studied in a lot more depth by Marie Curie. Marie Curie is awesome. She's one of my favorite physicists, although she's kind of straddles the line between physics and chemistry. She's actually the only person to ever win two Nobel Prizes in two different fields of science. She won it in physics for her work on radioactivity, and she also won it in chemistry for related to radioactivity, but she isolated and discovered the elements radium and polonium, two radioactive elements. So she did a lot of work on it. She was the first to determine that all that mattered, the only thing that affected the amount that the stuff was emitted was how much of the element you had. So more uranium equaled more of this radiation coming off of it. She also noticed that there was basically nothing you could do to stop it from radiating. No effect, no pressure differences, no temperature differences, not putting it in a vacuum, not putting it in air. No matter where it was emitting this stuff. And so she reasoned that it had to be coming from the atoms themselves. Again, this was another major step along with Thomson's electron discovery in proving that atoms were not indivisible. So Marie Curie actually had a really interesting life. I encourage you to read about it. She had faced a lot of trouble for being a woman in science. Again, you've probably noticed a lot of the scientists we've talked about are, well, old white guys, right? Science is not free of society. Science operates within society. And so a lot of the unfortunate inequalities that exist can hinder our advancement of science, and they have for hundreds of years. But Marie Curie did a lot in advancing and breaking through that. But we still have work to do, of course. So she actually coined the term radioactivity. What did it mean? It just meant something was emitting this stuff, this radiation. Okay. So we studied the properties of these high energy things, these things that were being emitted from certain materials, certain elements. And so we knew a lot about them, and we kind of had to give them names and talk about them before we actually knew what they were. A lot of them we found out were stuff that, well, we already knew what it was. We just didn't realize that was what was coming out. So there are names that have kind of stuck, placeholder names that have kind of stuck. While we were saying, okay, well, this is giving off this particle, let's call it an alpha particle. This thing is giving off this, let's call it a beta particle. And we would learn later that an alpha particle was actually a helium nucleus, and a beta negative particle was actually just an electron. We'll get into what those mean later. Just saying it now so that later when we start calling it a beta negative and it's also an electron, you don't say, well, why don't we just call it an electron? Well, we didn't know it was an electron, and we said it was a beta negative. So some of the stuff, turned out to be particles. So that is the case in alpha radiation, beta radiation, even some types of radiation even emit neutrons, okay? But some of the stuff turned out to be just good old EMR, okay? The main one that we're going to look at is gamma, but you can also have radiation that emits X-ray, high energy UV, technically all of them, but these are the ones that overpower the process, kind of. Okay, so we're talking about nuclear radiation. Nuclear radiation gets a bad rap. It's as soon as I say that, you're probably thinking scary. You see this image and you picture atomic bombs and you picture Chernobyl, okay? Well, it's a lot of energy, so of course it can be used in poor ways, but it also has a lot of incredible applications, okay? So nuclear radiation is behind nuclear power, which is a good thing. Nuclear power is a very clean source of energy. It has its downfalls like all other forms of energy. Its biggest one is that the products of nuclear power, the leftovers, the byproducts, are themselves radioactive, and so they're kind of unsafe. You have to figure out how to store them. However, there's new work being done with different kinds of radioactivity, namely thorium, which the decay products are actually quite stable and not radioactive. So that could be a huge step forward in our advancement of nuclear power. Okay, cancer treatment, radiation therapy. Radiation can target cancerous cells better than it targets healthy cells. So that's a good application, okay? But it can also cause cancer. So obviously that is bad. We'll just look a little bit at how that happens. It's used to sterilize medical instruments. It's used to irradiate food to kill any bacteria, insects, things like that. So most of the food you eat has been irradiated at some point. And that's what allows it to keep so long. The oranges that you get from Florida, good luck just driving with a bag of oranges from Florida to Alberta and them not going rotten. They need to be irradiated first. Okay, radiation sickness comes from a dose of too much radiation. Nuclear meltdowns, like in Chernobyl, that one has scared people off of nuclear power forever. Nuclear power is really quite safe. Chernobyl, there was a lot of corners cut, a lot of safety measures that were not followed, and the result was a catastrophe. Okay, nuclear bombs, when that amount of energy is put into warfare, you can get some pretty bad results, obviously. Okay, but nuclear radiation actually supports all life on Earth, which I would count as a positive of nuclear radiation, right? You would not be here without nuclear reactions producing energy, because that is how the sun produces energy. We'll talk about that a bit later too. You are actually exposed to nuclear radiation constantly. Okay, right now you are being hit with nuclear radiation. There's nuclear radiation from the sun. Eating a banana will actually give you a decent dose of radiation because there are isotopes of potassium in it that are radioactive. So why does it have such a bad connotation? Well, it's when you receive too much all at once that it becomes dangerous. Now, all of these processes really have to do with ionization. Remember, in physics, ionization basically always means an electron gets kicked out. So high energy waves and particles, like the ones involved in radioactivity, they have enough energy to ionize atom, which obviously gives them a charge. The ionized atom, better known as just an ion, okay, will bond chemically very quickly, but maybe not appropriately. So it will bond quickly, but it's just going to bond to the first thing it kind of sees a lot of the time, right? And so you can see why this might be dangerous, because think of chemistry, right? Slightly different bonds make huge differences in the properties of matter. For example, you'll die if you don't drink H2O, water, but if you drink H2O2, you will die, right? Hydrogen peroxide, okay? Now this is kind of missing a segue here, but it's saying, so I'll just add it in. Okay, so radiation from the sun can damage DNA molecules. If you do it a little bit, you get a tan. If you do it too much, you get a sunburn. Okay, but most of the time the DNA is so damaged that it cannot reproduce and the cell simply dies. It happens all the time. Even right now, it's happening to you. And most of the time, nothing happens. But if one is exposed to too much radiation all at once, too many cells can die too fast for the body to replenish. So that's useful in the process of sterilization if you're trying to kill all the bacteria on a surgical scalpel or something like that. It's obviously bad, though, if a human being is exposed to a huge dose of radiation and causes cell death. Every now and then, though, the cell is damaged a little bit, but not so much that it can't reproduce. And so it reproduces. But in that damaging process, when it got put back together, basically, it didn't get put back together quite correctly. And so it reproduces, but it doesn't know when to stop. Usually there's something that says, okay, stop doing mitosis, cells, stop growing. But if a cell is damaged the right way, that off switch isn't there. And so it just grows and 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 reproduces and reproduces and reproduces. And we call that a tumor. So you can see here, ionizing radiation comes in, affects the nucleus of the cell, okay? Not a nucleus like we've been talking about in an atom. This is made of billions of atoms, but the term nucleus kind of fits, right? You can kind of see how the nucleus of a cell is like the nucleus of an atom. And the DNA in the nucleus can get messed up, and when it gets put back together, it grows, and it doesn't know when to stop. And that is when you have a tumor. So that was just a quick note on radiation and whether it's a good or a bad thing. And the answer to that is that it depends on what it's being used for, or how it's being used, or how you're being exposed to it. All right, so physicists were studying this radiation, this stuff that was coming off of certain elements, certain materials, and they found that there were 3 different types. The way they did this was how we do a lot of studies on particles, see how they behave in an electric and magnetic field. The first one that they found, they called it alpha, because alpha is the first letter in the Greek alphabet. So they said this is alpha radiation. And so we'll just do a general overview right now. We'll go into more detail later, but just so you can see the 3 types, we have alpha radiation, ejected with extremely high speeds, made of a helium nuclei. We now know, of course, they didn't know that at the time. It had very poor penetration power, okay? It can only travel a few centimeters in air, and it would be blocked even by a piece of paper because it's big. It's a pretty big piece of radiation. It's a positive particle, and it will behave as such in B and E fields. That's how we knew it was positive. So again, it's the easiest to shield, but it can be quite harmful. In fact, even the most harmful if it's not blocked. Why? It's the biggest of the 3 we're going to look at. It has the most chance of messing with your DNA if it is allowed to get in there. But even the top layer of your skin, which is mostly dead anyway, will actually completely block an alpha particle. So for the most part, we're safe from it. If you were to swallow a pill full of alpha radiating material, that would be bad news, right? The bigger it is, the more of a collision it's going to cause when it hits you. Okay, beta radiation. It was the second one they found, so they said, let's call it beta, the second letter of the Greek alphabet. So these are actually high energy electrons or positrons, more on that later, have greater penetration than alpha. They can actually travel 1/2 meter or more in air and then get blocked. So you're still not talking about great penetration, right? Air is going to block it, just air. But in most materials, it can actually go in a few centimeters. So this can actually penetrate into you a little bit, like a few centimeters, but it has much less ionizing potential because, as you know, an electron is much smaller than even a proton, let alone 2 protons and 2 neutrons, which is an alpha particle. Okay, so it's not as easy to shield, but it's not as harmful as alpha either. So they behave as particles. They're either negative or positive, depending on whether they're an electron or positron. Notice positron, not proton. Okay, 2 different things. We'll talk about what that is in a sec. Okay, and these will make sense later as well. Gamma radiation, yes, the same gamma that you know from EMR. The name came up because gamma is the 3rd letter in the Greek alphabet, and that's why most of the parts of the EMR spectrum have nothing to do with Greek letters, and then randomly you have gamma thrown in because it actually came from here, where we discovered it as the 3rd type of radiation that came from stuff, and it is exactly what it sounds like. It's high energy EMR, it's gamma rays. Okay, it is the highest penetration. It can only be blocked by things like a thick piece of lead, and lead is very good at stopping stuff. When Marie Curie died, actually, they had to bury her in a lead coffin because she worked her entire life with very radioactive materials before they understood the dangers of working with radioactive materials, and her body will be dangerously radioactive for the next like 5,000 years or something like that. If you want to read her papers, you have to put on a hazmat suit, all that, because they're all contaminated with polonium. And unfortunately, it is what ended up killing Marie Curie. She got leukemia at a relatively young age because of her work with all these radioactive materials. So in theory, gamma radiation is the least damaging because, again, it's the smallest. It's most likely to just pass through your particles without hitting anything, unlike an alpha particle, which is like a bull in a china shop, right? But since it's so penetrating, it actually is often kind of considered one of the more dangerous ones because you can't stop it. If there is a gamma radiation source next to you, remember, if there's 3 sources of radiation outside of your body, alpha, beta, and gamma, alpha is not even going to get into you. Beta might get a few centimeters into you. If alpha could damage you, it would, but it can't. It gets blocked. Gamma is the least likely to damage you, but it's also the most likely to go through your body. And so if it's outside of your body, gamma radiation is actually the most dangerous because of its penetrating power. Okay, so let's go into detail on first alpha decay. So we kind of brushed over this. What is happening here? Why are certain elements giving off this weird radiation? Okay, well, remember that the nucleus contains protons repelling each other and neutrons that don't do anything. They don't repel or attract. And why does it not all fall apart? Well, because of the strong nuclear force. It holds the nucleus together, and that is fighting the electrostatic force. So essentially, a nucleus's entire life is a battle between the electrostatic trying to rip it apart and the strong nuclear trying to hold it together. But the thing is, the nuclear force only acts over a very small distances. The equation that describes the strong nuclear force is very complex, but you can roughly approximate it as being proportional to 1 over r to the power of 12, right? Whereas the electrostatic is 1 over r squared. Now, truthfully, as just an approximation, the nuclear force is not like the electrostatic or gravitational, where it actually has an infinite range, and it would get very, very, very small across huge distances, but it would never be 0. That's not how the strong nuclear force works, actually. The strong nuclear force actually does become 0 outside of a certain distance, and it's a small distance. So in large elements, specifically ones that are bigger than lead, that's nothing special about lead, that's just where it starts to become too big. The nuclear force, it doesn't have the range. It's such a small range that it can't even reach across the same nucleus and keep those ones together. So they start to get too far apart from each other. And the nuclear force cannot keep the nucleus together, and the electrostatic force, quote unquote, wins. Okay, and it flies apart. So this is an important definition here. When an atom or an isotope of an atom has a strong force capable of keeping its nucleus intact, we say it is a stable atom for obvious reasons, right? It will continue to exist. But if this is not the case, if the electrostatic force is inevitably going to beat the strong force, then the atom is unstable and it will decay into something that is more stable. So how does it do this? Well, the first way we're going to look at is by emitting an alpha particle or a helium nucleus. Okay, so you really do just start with, we call this in all types of radiation we're going to look at, you start with a parent, which becomes a daughter nucleus. And you can see the start of the emission here, right? An alpha particle is emitting. And then afterwards, you have your daughter nucleus, which is stable, and your alpha particle, which is leaving with whatever kinetic energy comes from the change in binding energy that has happened between this thing and this thing. Because remember, every atom has a different binding energy based on the mass deficit between the nucleons when they're bound and the nucleons when they were free. Okay, so that really is what alpha decay is. It's a radioactive element. It undergoes alpha decay. And what is alpha decay? It's it losing 2 protons and 2 neutrons. Stop and think here for a sec. What makes an atom that atom? What have we said is the rule that you have to follow to be that atom? You have to have X number of protons, right? If you want to be plutonium, you need to have 94 protons. What did we just say it's going to do? It's going to lose 2 protons. So it's not going to be plutonium anymore. It's going to be uranium. So literally, it is changing identities. One element is becoming a different element. This is not a chemical reaction in which one element joins another to make a compound. No, one element is becoming a different element. This is a alchemist's dream, right? This is what alchemists were trying to do forever, transform, well, pretty much everything they could get their hands on into gold. So why does this happen? Because uranium is more stable than plutonium. You would say it decays by alpha particle emission. All right, so some general physics principles that are going to apply to all 3 types of radiation we're going to look at, okay, but we'll mention them here since we're doing it the first one. So always consider the conservation of charge. So in other words, the total charge before, if you add up all the charges before, it must equal the total charges after. So for example, looking at this one, plutonium got rid of an alpha particle, which is 2 protons. But we're okay because now this has 2 less protons. So 92 plus from the 92 protons and 2 plus from the 2 protons here gives you 94 plus like you had with the plutonium. So we're good. Conservation of charge has been obeyed. The other one is the conservation of nucleons, which means the total number of protons and neutrons before must equal the total number of protons and neutrons after. Notice it's not conservation of protons. Notice it's not conservation of neutrons. It's conservation of nucleons. You'll see why when we do beta decay. Things are going to get even weirder. Okay, in other words, all of the A's before must be all the same as all of the A's after, A being the atomic mass. So the conservation of nucleons is kind of similar to the conservation of mass, but you're not allowed to call it that because mass is not being conserved, right? We've seen that already. However, mass energy will be conserved, which is physics principle number 6. Again, you know that since I'm saying that it's okay to have fewer protons as long as you have the same amount of more neutrons, you know mass can't be conserved because you know that neutrons have a slightly larger mass than a proton, right? However, mass energy, which is literally just all the mass and all the energy added up, that before must be the same as that after. Okay, here's the general form for an alpha decay reaction. It will always look like that. Let's check here our conservation of charge and our conservation of nucleons. How many nucleons do we have before? A, right? That is the number of protons and neutrons. That is the number of nucleons. How many do we have after? Well, we have A minus 4 and 4. That's not a coincidence, right? Why is it A minus 4? Because it lost 4 when this alpha particle left. So A equals A minus 4 plus 4 by physics principle number 8. Okay, so we're good. This is a way you can check your work. This will always hold. What about conservation of charge? Well, we need to see, does the total charge add up? Okay, well, the charge here, there's no electrons involved. The charge is just coming from protons. Right? We're not necessarily dealing with whole atoms here. We're really dealing with nuclei, right? Besides, electrons are not really going to be involved. At least the electrons that quote unquote orbit the shell. Those electrons are not involved. There are going to be electrons here, but it's not those ones. For conservation of charge, we have plus Z from all the protons, and then we have plus Z minus 2, and then we have plus 2 on the alpha particles. So does plus Z equal plus Z minus 2 plus 2? Yes, it does, because those 2's would just cancel. So this works out, and that is a way of checking with physics principle number 7. Okay, so let's just get some practice with this. Write the decay reaction for radium-227 if it undergoes alpha decay. So you will definitely need your periodic table for this. I know I didn't give you one in class, but the digital version of the data booklet that I posted does have it on there. So start with the symbol. Okay, that'll be easiest. We know we're going to have radium. Okay, and it's radium 227. So don't forget, this is the atomic mass. And if you did forget, it's on your periodic table as well. It's not the atomic number, okay? The atomic number is on your periodic table, which is good because they didn't give it to us. But radium always has the same atomic number. It wouldn't be radium. And for radium, that is 88. Now it undergoes alpha decay. So what does that mean? Well, like you saw in the picture, this thing, this parent nucleus, is going to become some daughter and an alpha particle. So that's the symbol alpha, the Greek letter alpha. It's okay to say He for helium, but usually when we're talking about radiation, we do stick with the old name of alpha particle. Okay, so why did I do that? Well, now we can figure out conservation of nucleons. How many do we need to end up with? These 227 cannot have been created or destroyed, and there's 4 here in this alpha particle, so there must be something here with 223 nucleons. There we go. 223 plus 4 is 227. We're good. But also conservation of charge. Right now we have plus 2 from an alpha particle, those 2 protons. Here we have plus 88 in radium. So what must the atomic number of this thing be? How many protons must it have? Well, it must have 86. And now 88 is equal to 86 plus 82. 227 is equal to 223 plus 4. Good. We've done our checks on physics principles number 7 and 8. And so all that's left to do now is go to your periodic table and figure out, hey, what has 86 protons? And you will see that it is radon, Rn. Okay, something unknown, ooh, mysterious, decays into cesium-141 and an alpha particle. All right, then let's find out who you are, Mr. or Mrs. Unknown. It decays into cesium-141 and an alpha particle. So we'll start with that. Cesium-141. So you have to check on your periodic table again for what is the atomic number for cesium, but you will see that it is 55, okay? And an alpha particle. So we got to figure out, okay, conservation of nucleons. We now have this many nucleons on our after side of the equation. So we must have started with 141 plus 4, 145 nucleons, right? Now, conservation of charge, we've got 55 positive protons here, 2 positive protons in our alpha particle. So that's 55 plus 2, 57. So what has 57 protons? Only one thing has 57 protons, and it is lanthanum. So it's not so bad, right? That's kind of all there is to it. So that's really all it is just counting up your nucleons and your charges. We're going to do it in different ways, but it's always the same idea underneath. If barium-144 undergoes alpha decay, what is the name of the resulting daughter nucleus? So the parent is barium, the daughter is question mark. So we'll start with what we got. We got barium-144, and that's undergoing alpha decay, so that's our before, that's our parent. Check the periodic table, and barium has an atomic number of 56. It's going to undergo alpha decay. So definitely an alpha particle will be produced. And we want to know, well, what is the daughter here? Okay, now be careful here. Don't get too comfortable, because a common mistake would be to go 144 plus 4. No, remember, you're trying to keep those two sides balanced, right? So if you put 148 over here, now you've got 152. That's too many, right? So you kind of need to backwards think. Okay, so if I have 144 total before, I need to have 144 total after. I've already got 4. That means I just need 140 more nucleons, okay? I had 56 protons at the beginning. Afterwards, 2 are already accounted for in the alpha particle, so I'm missing 54 more. And what has 54 protons? Only xenons. That's pretty much it for alpha decay. Okay, moving on, beta decay. So again, the cause here is just the instability of the atom or the... So again here, the cause is just the instability of the atom or isotope. It doesn't want to exist, okay? So a nucleus, again, is a constant tug of war between the strong and electrostatic forces. Okay, but the mechanism behind its instability is fundamentally the same. It's because of a battle between the strong and electrostatic forces. However, the way it plays out is a bit different. It doesn't just pop off an alpha particle. So don't forget, it's a tug of war between the strong and electrostatic forces. In the battle against the electrostatic force, it would help the strong nuclear force keep the nucleus together if you added a few more neutrons, you would think, right? Because you can't add neutrons without forcing the protons to spread out a bit. And if they're spread out a bit, we know the electrostatic force is proportional to 1 over r squared. So the electrostatic force will get a bit weaker. A little bit of a break for the strong nuclear force, right? Right. But every time you add a neutron, you increase the size of the nucleus, right? And if you do that too much, remember the strong nuclear force only acts over very small distances. And what was the whole reason alpha radiation happened? Because the nucleus was too big. The strong nuclear force couldn't act over that much distance. So you kind of see there's a give and take here, right? There's kind of a delicate balancing act going on within a nucleus in which only just the right ratio of protons and neutrons will result in stability. Too many neutrons, the strong force can't hold it together because it's too big. Too few neutrons, the protons are too close, and the electrostatic force causes decay because it's so strong at smaller distances. So there's another way an unstable atom can become stable, okay? And it sounds bonkers at first. It kind of is bonkers. It's a process that is actually not even completely understood to this day. We've obviously got a lot more understanding of it, but it is still one of those things that does leave us scratching our heads sometimes. Essentially, since what we need to find here is the right balance between protons and neutrons, well, a form of radioactive decay can occur in which a proton changes into a neutron, or vice versa, a neutron changes into a proton to get a more stable ratio. Got too many protons, not enough neutrons? No problem. Turn one of your protons into a neutron. Okay, it sounds nuts. It kind of is. It blows my mind a little bit. And yet it happens. Fun fact, by the way, we got 3 of the 4 fundamental forces down, right? We did gravitational, electrostatic, and strong. Well, meet the last one, the weak nuclear force. Now, the weak nuclear force is not weak. It's much, much, much stronger than gravity, okay? However, it is weaker than the strong nuclear force. So again, physicists, ever the poets that they are, decided to call it the weak nuclear force. How does the weak nuclear force mediate this? It's pretty complicated. It has to do with quarks and stuff that we're going to talk about in chapter 17. Truthfully, we're not going to get that far into the weak nuclear force, but you can read up more if you want. Okay, so there are 2 types of beta decay. Okay, only one type of alpha decay, but there are 2 types of beta decay. And you might be guessing why, because we said sometimes a proton becomes a neutron, sometimes a neutron becomes a proton. Those are 2 different types of processes. And so in beta negative decay, a proton becomes a neutron. So this is how it looks, right? You have a unstable nucleus, a carbon-14 nucleus that is unstable. How can it become stable? Well, why is it unstable? It's just got the wrong ratio. It's not necessarily too big. It's just got the wrong ratio. It would feel a lot better if one of its neutrons were just a proton. And so it does that. It kicks out what we call a beta negative particle, which you know better as an electron. Now I want to be clear here right off the bat. This electron is not an electron that's orbiting the nucleus. It's not one of carbon's electrons. In fact, this electron did not exist before this happened. The electron is a product of the decay process. So in moving to that more stable nucleus from carbon-14 to nitrogen-14, it loses energy. Where did that energy go? Some of it went into the mass of the electron, right? E equals mc squared, mass energy equivalence. Okay, that is a new electron that did not exist before the decay. It was not just hiding in the nucleus. It literally popped out of the pure energy that came from going to a more stable configuration. Just like the photon that seemed to pop into existence when the electron was de-excited in Bohr's model from last week. Okay, so it didn't exist, it at least didn't exist as an electron. You could make an argument that it existed as the energy, but not really, right? Okay, so again, just follow those conservation laws. We're going to do things a little bit differently, but at the same time, we're not going to do things differently. We're just going to make sure we have the same number of nucleons and the same charge. But now that an electron is involved, you can think charge, okay, charge is going to be a little bit different. So again, the basics, a neutron becomes a proton. How does a neutron become a proton? Well, it has to become more positive, right? Now, another way of saying more positive is by getting less negative, right? So by getting less negative, what do you have to do? You have to kick out something negative. You got to get rid of something negative. So it gets rid of something negative in the form of a beta negative particle, aka an electron, spits one out. And now technically that would satisfy our 2 conservation laws. However, there is something else that is produced, and it purely just comes from observations. We notice that this electron is going way too slow, right? We know the difference between the binding energy of carbon-14 and the binding energy of nitrogen-14. And we said, okay, this electron's going to come out super fast because there's this much energy difference. And if it's all going to a tiny electron, well, that electron better be ripping to have enough kinetic energy. And it didn't. It was going way too slow. And so we eventually came to realize there was a tiny little, tiny, very small mass particle called an antineutrino, okay? Neutrino is literally Italian for little neutral one. I think that's adorable, okay? And it's just emitted to allow for momentum and energy to be conserved. So you do just kind of have to remember this, okay? It's just got to be memorized that in beta negative, an antineutrino is produced. In both types of beta, some kind of neutrino is produced. I remember that it's an antineutrino because that little line above it, that means anti. It means it's an antiparticle. And so I think of the little line above as a negative sign to help me remember that it happens during beta negative decay. Beta positive decay, you just get a plain old neutrino. Okay, by the way, what does that mean, that anti? I've kind of brushed over it. You may have heard of matter and antimatter. So for every fundamental particle that exists, there is an anti-version of that particle. There's an antiparticle. So there's our neutrinos, there are antineutrinos. What is an antiparticle? Essentially everything about it, like mass, all of that stuff is the same. The mass of a particle and an antiparticle will be the same, but the charge is the opposite, and other properties that we don't really cover in physics 30, but will come up later in your physics education. Something called the spin, for example, which is in the case of the neutrino, because it has no charge. So if it were to have what's the opposite of zero is still zero, right? But it does have the opposite spin of a neutrino. So a neutrino and an antineutrino have opposite spins, and they are antiparticles. It is a property of every particle, just like charge, just like mass. Every particle has a spin, and an antineutrino has the opposite spin of a neutrino. It's not actually like it's spinning, but that's kind of how physicists conceptualize it. By the way, why don't you see much antimatter? Well, physicists theorize at the beginning of the universe, matter and antimatter basically existed in equal proportions. The thing about matter and antimatter is when they meet each other, they completely annihilate into pure energy, right? You can imagine that's a lot of energy being released, because by E equals mc squared, 100% of the mass basically becomes energy. Now, at some point at the beginning of the universe, for whatever reason, that's a topic of ongoing research, matter won out. And so we are all made of atoms, not anti-atoms. To date, we've only ever succeeded in making about 8 anti-hydrogen atoms, which is made of a anti-proton and an anti-electron, which is called a positron. We'll get to that in our next type of decay here. It's pretty rare stuff, and it's very hard to handle because, like we said, if it comes into contact with any regular matter, which of course is everywhere, it annihilates. What do you need to know about it for physics 30? Just that it's emitted during beta negative. Okay, so remember the line above means antineutrino, and I think of that line as a minus sign so that I remember it happens during beta negative decay. And actually, big issue here, it's missing from the diagram above, so add it. Okay, we will. It should not just emit a beta negative, it should emit a antineutrino. There we go. And what I said about the beta particle still goes for the antineutrino, okay? It was not hiding inside the nucleus. It is a product of this reaction. It was not just waiting to get popped out. It was created from the energy that it came from the mass defect between carbon-14 and nitrogen-14. Okay, so let's just take a look at the general form here. Again, physics principle number 7, physics principle number 8, conservation of nucleons. So we have A nucleons at the beginning, we need to have A nucleons at the end. So check. We have A before. Does that equal A plus 0? Whoops, plus 0, right? Why does a beta particle have an atomic mass of 0? Well, you tell me, is an electron a nucleon? Is an electron a proton or neutron? No, right? It's not. It should be a 0, right? We don't write the zeros in here, but same thing goes for the antineutrino. It's not a proton or a neutron, so it's not a nucleon, okay? And does A equal A plus 0? You bet it does. And so we are good by physics principle number. Okay, conservation of charge. You see what I mean, right? So we started with a charge of Z plus Z, right? Because these are all protons. Its neutron is becoming a proton. That's why it's Z plus 1 after, right? The daughter nucleus has a charge of Z plus 1 because what used to be a neutron is now a proton. There's one extra proton. Charge would not be conserved unless something negative was created to counter that. And sure enough, beta negative decay, we're good, right? So plus Z does equal plus Z plus 1 minus 1 because the 1s will go away. And so we're good. Okay. Hey, it's the reaction we were just looking at. So unstable carbon-14. So carbon-14 stabilizes. So let's start there. It's carbon-14. It has 14 nucleons. And it's carbon, so it always has 6 protons, an atomic number of 6, Z. Stabilizes by undergoing beta negative decay. So how about we just start there with the beta negative decay? So beta, yes, we know it's just an electron, but we usually go by the old name of beta decay. Now, it's not a nucleon, so an electron has 0 nucleons in it, right? But it does have, I know Z is atomic number, but you can think of Z as more like the number of protons, or even more generally, the number of positive charges. So how many positive charges does a negative charge have? Well, it doesn't have 0. It has less than 0. It has -1 positive charges, okay? And we're trying to figure out what it is. Now, we kind of spoiled this already, but let's see how we would do it if we didn't know what it was going to be. We started out with 14 nucleons. How many nucleons do we have to have at the end? 14. Okay, we started out with an overall charge, or an overall number of positive charges, of 6. So far, we've got -1. Uh-oh. So we need this plus this to equal this, 6, right? So -1 plus 7. Well, that equals 6, right? -7 minus 1 is 6. So this is 14, 7. What has 7 protons? Only one thing, and that one thing is nitrogen, okay? This is actually the equation that is used in carbon dating. We'll see that later. And kind of just a thing you have to remember, okay, don't forget the antineutrino. Okay, in a rarer double beta negative decay, germanium-76 transmutes to selenium-76. Okay, so a good hint that this is going to be beta decay is that the name of the element changed, right? So the number of protons must have changed, but the atomic mass didn't change. So the total number of nucleons can't have changed. That's right up beta decay's alley, because no nucleons have left the nucleus. They've just changed from being a neutron to a proton, or from a proton to a neutron, so that the number of nucleons stays the same. So let's start with this, germanium-76. So that is, and germanium always has 32 protons, and it's going to transmute to selenium-76. So let's start there. And if you look on the periodic table, you'll notice selenium has an atomic number of not 33, but 34. So how did this happen? Well, germanium gained 2 protons without losing any nucleons, right? Still got all 76. So 2 neutrons became 2 protons. That's the only way to explain it. How did it do that? Well, it for sure would have had to emit a beta negative particle, okay? But it actually would have emitted, but it did that twice, right? It did that twice. So we would say plus 2 beta negative particles. Okay, how many antineutrinos do you think were produced? That's right. Every time beta negative decay happens, an antineutrino is produced. So if it happens twice at once, well then 2 antineutrinos are produced at once. Okay, quick check on conservation of nucleons. I have 76 before, and I have 76 plus 0 plus 0. Good, that works. 32 positive charges before. After I have 34 positive charges, but I have 2 negative charges in the beta negative particle, the electrons. So, okay, beta positive. So this is when a neutron becomes a proton. So here's the general idea, okay? You can see this proton here. The ratio isn't quite right. It doesn't have the right mix of protons and neutrons. So it says, I'm going to make a proton a neutron, and that's better. Now I'm stable, okay? Now it does that by emitting something called a positron, not a proton, a positron. What is a positron? It is the antiparticle, remember we were talking about those, of an electron. It is an electron's antiparticle. Everything about a positron, mass, all that is the exact same, except its charge is plus 1. Kind of weird, eh? Okay, so a positron is just the antiparticle of an electron. So essentially, take what you know about beta negative and flip pretty much everything, okay? So instead of a neutron becoming a proton becomes a neutron. Hey, so a proton's gonna become a neutron, so it's gonna go from plus 1 to 0. So in other words, it's getting less positive. How do you get less positive? You gotta kick positive stuff out, right? So kick out a positive positron. So a beta positive particle, also known as a positron, which again is just the antimatter version of an electron, is emitted just like the electron was emitted before. And now instead of an antineutrino, a regular old neutrino without a line above it, because the line above it means anti, okay? And it's just emitted, again, to allow for momentum and energy to be conserved. Once again, it's missing from this diagram, so let's go ahead and add a little neutral neutrino. Whoa, not an antineutrino. a neutrino. Okay, so in general form, pretty much everything's the same, except now you have a proton going to a neutron, so the charge decreases by 1, right? And that's okay because you have a positron being emitted, which makes up for that. Let's use the general form here to once again do a quick check on our physics principles. We have A before, and we're wondering if that's equal to all of the nucleons after. So yes, A equals A plus 0, okay? Then for charge, we're wondering if Z is equal to positive Z minus 1, because there's one less positive charge, but there's one more positive charge in the plus 1, so those ones would cancel, we're good. So iodine 125 undergoes positron emission, write the nuclear reaction, so they're not even going to tell us what the daughter is, but they tell us it undergoes positron emission, so we have a beta positive particle. Now it is not a nucleon, so that is still 0, but it does have a charge of plus 1. Okay, I know it seems weird. Think of this as the number of positive charges, not so much as the number of protons, okay, because really that's kind of what it is. Plus, okay, conservation of nucleons. The neutrino is not going to do it, so it's going to have to be all from the daughter. 53 positive, positive 1, this thing must have 52 protons. Therefore, it is tellurium. Quick check, 125, 0 plus 125, we're good. 53, 1, and 52 is 53, we're good. Okay, what is the parent nucleus that will result in an oxygen-16 daughter if that parent underwent beta positive decay? Okay, so we're wondering what the parent is. Start with what we got. Okay, so we obviously had 16 nucleons before. We had 9 positive charges, and so this must have been, from the periodic table, atomic number 9 is always fluorine. Okay, a proton undergoes beta positive decay to become a neutron. Okay, so you can represent this with a nuclear reaction equation. Essentially what we're doing here is just representing beta positive decay, because that's what it is. It's a proton becoming a neutron, right? So how would we do that? We would say, now how many nucleons is a proton? It's 1. A proton is a nucleon, right? What's its charge? How many positive charges does it have in it? 1. Now it undergoes beta positive decay, so this proton becomes a beta positive particle. How many nucleons is a beta positive particle? None. There's no positrons in the nucleus, but it does have a charge of plus 1. And it also becomes a neutron. So you can kind of do this even just with your knowledge of what the things are without even checking the conservation laws. In fact, let's do that. How many nucleons are in a neutron? 1, because a neutron is in the nucleus. And how many positive charges does a neutron have? 0, right? So let's check now with our conservation laws. We have 1 nucleon before. We have 0 plus 1 is 1 nucleon after. Hey, we're good. We have 1 positive charge before, and we have 1 plus 0 is still 1 overall positive charge after. We are good by our conservation laws. Okay, the third and final one is gamma decay. And it's a pretty different process. But again, we were just finding these things. We said, hey, this one's doing this stuff. Call it alpha. This one's doing this one. Call it beta. This one's doing this one. Call it gamma. Okay, so gamma radiation occurs after alpha or beta decay. So alpha or beta decay happens, and then a gamma will occur, usually. So since gamma radiation only involves the emission of a photon or many photons, but either way, it's just EMR, right? No transmutation occurs, right? Transmutation, again, is when an element goes from being one element to another, and no particles are emitted. So what's the point of it then? Why bother, right? If you're not going to be getting rid of protons or neutrons and becoming a more stable nucleus, what's the problem? Well, you are still becoming more stable, because remember, the more stable arrangement does get rid of binding energy. So essentially, after the alpha or beta decay, you could think of it like it's all shook up, right? It just violently emitted a part of itself, or at least changed itself from a proton to a neutron. And you can even think of it this way. If a neutron becomes a proton, well, that proton might be right next to a proton now. And so the nucleus kind of needs to shift itself to get in the right, to distance those protons from each other. So the daughter nucleus is often formed in an excited state. It has excess energy. It wants to get rid of it. So a lot like the electrons that we talked about in the Bohr atom, it's actually a very apt comparison. Okay, it returns to a quote unquote ground state by emitting a high energy gamma photon or photons and basically reshuffling its nucleons. Okay, it's a burst of just energy. It's all hyped up and it just kind of burps it all out as one big burst of gamma ray energy. Why gamma ray? Well, relatively a lot amount of energy to get rid of. You'll remember gamma is the lowest wavelength, the highest frequency, and therefore the highest energy form of radiation. That's why this can be so damaging. Yes, it has the least ionizing potential of the three we've looked at, but it still has a lot of energy, and it's also the most penetrating. So just a reminder, all EMR is produced by accelerating charges. Here, the charges are the protons in the nucleus as they reshuffle. And it's a big acceleration. It happens pretty much instantaneously. So it's a lot of charge shuffling very quickly. You can imagine why that would produce a big blast of gamma radiation. Okay, like we said though, no transmutation, nothing changes. All that we're getting rid of here is energy. So all that really happens is you produce a photon of gamma radiation. That is the symbol for gamma radiation. It's the Greek letter gamma. So for an example of an actual gamma radiation that happens, sometimes something that can be a product of radioactive decay is iodine 125, and that can be formed with a lot of extra energy, so it gets rid of it, but nothing changes about it. It just reshuffles, and in doing so emits a high energy gamma photon. Okay, so just kind of wrapping up here, a comparison of the penetration. It's important to understand from a protection and risk analysis standpoint, because this stuff, when mistreated, as we've seen in Chernobyl, can be harmful. When used well, it can be very useful. So as you can see here, right, this is when we say tissue, like literally tissue, okay? Alpha particles cannot penetrate that. Beta particles can get through that, but they're going to get stopped by other stuff pretty much right away, right? Gamma particles, on the other hand, you basically need lead to stop it. So there's a give and take here in terms of danger, because from least to most penetrating, they also go from most to least ionizing. So which one will cause the most damage? Why? Alpha, because it's so much bigger. It's like a cannonball hitting your DNA. So it is the most damaging. It's just so easy to block that we actually don't worry about it too much most of the time. However, if it's outside of your body, it probably won't do you much harm. It's going to get blocked even just by the top layer of your skin, which is dead anyway. Okay, if you swallow a pill full of alpha particles, full of alpha radiating material, well, bad idea. But don't do that and you're probably fine. What is easiest to protect yourself from? The thing that makes it dangerous is the thing that makes it easy to protect against. Because it's so massive and so likely to ionize, you can block massive things really easy. It's the small high energy gamma radiation that can sneak through whatever you try to use to block it. It's very likely to collide. So it will collide with the things that you put to stop it from hitting you. Right? And then the inverse is true for gamma. It's the smallest, so it's the most likely to pass through. However, that can make it dangerous to deal with because it's the most likely to pass through, right? It has a good chance of going through you, causing no harm, but it also will go through anything you use to protect yourself from it, except lead. Beta particles fall somewhere in the middle. They'll go through your shirt or your clothes or whatever, and they'll pass through most of your particles. They're kind of in between the two, right? So they're not the most dangerous, the most risk of ionizing. They're pretty easy to block, but they can go through some stuff. They could go through your shirt, but they wouldn't go through, say, a textbook. All right, so like we mentioned at the beginning, now that we know what these particles are, we can think about how they would behave and kind of retrace the steps of scientists who were looking at them and trying to figure out what they were and how they were made up, okay? And that just came down to seeing how they behave in different fields. So it asks us to draw in what a positron would do in the shown field. So a positron, again, everything about it is the same as an electron, except its charge. Reminder of how to deal with these types of questions. Remember, this magnetic force is going to cause circular motion. So the magnetic force is acting as a centripetal force. And what we're doing when we're drawing the path is figuring out what the radius looks like, right? So solving this, R is equal to mv over qb. So really, assuming we're sending them all in at the same speed and that the magnetic field is uniform, all this depends on is the mass and the charge, right? So we have to compare those. So here's what a beta negative did. How do I know it was beta negative? Well, this is described by the left hand rule, right? Thumb towards the top of the page, fingers into the page because those are X's, and your palm will be kind of scooching it this way constantly. That's the magnetic force. So a positron will do the exact same thing because it's got the same mass, it's got the same charge. You're just going to have to pull out your right hand because it has a positive charge. It has the same magnitude of charge, I should say, right? So a positron will go like that. Same radius, just in the opposite direction. Okay, in an electric field, how do we deal with the paths here? Well, what do they depend on? In an electric field, we basically have parabolic motion, right? It's a lot like projectile motion. So essentially, it's just that they're going to accelerate because of a net force. And what is that net force? The electrostatic force. We can basically ignore gravity. It's not going to matter. So we are in between two parallel plates, so that would make us use this one, right? The charge times the force per unit charge. And so what is going to determine its path? Well, it's just going to be the acceleration that it feels side to side, right? Because the more strongly it gets pulled this way, they all have the same sideways speed. So if it's accelerating more, right, then that way. Or if it's accelerating less, then it has longer to keep moving in this axis. So all it really comes down to is which one has the biggest acceleration to the side. So it depends, once again, on the charge and the mass. So if it has a bigger charge, it will accelerate more. So again, we're going to compare to our beta negative here. We know it's beta negative because it's going towards the positive plate. A positron has the exact same mass and the exact same charge, just the positive version of it. So it will have the same magnitude of acceleration, right? Just in the other direction. It's going to feel the electric field in the direction that the electric field actually is, because again, it's defined as what a positive charge would do. Okay, pause here for a second to compare the curves of other ones. Notice the alpha particle, the heaviest of them all, right? Biggest mass, so biggest radius. It also has a bigger charge, but a slightly bigger charge, which would make its radius smaller. But remember, the factor by which its mass is bigger than an electron's versus the factor by which its charge is bigger than an electron's. Its charge is twice as big as the electrons. Yes, that's true. Its mass is 3,600 times larger than the electrons. So forget about it, right? In fact, this is not even drawn to scale. This should look more like that if we were going to do it realistically, okay? Also notice what the gamma particles do, and is that what you would expect? What's the charge on a gamma quote-unquote particle? What is a gamma particle? It's a photon, right? It's a gamma photon. Photons don't have charges, so it should pass undeflected through a magnetic field, and it should pass undeflected through an electric field. Okay, let's do this one really quick. Redraw the above experimental setups. Include all 4 types of nuclear radiation we have discussed, but this time with the magnetic field pointing out of the page and the electric field from left to right. Okay, so starting with the magnetic, and let's just start with the alpha particle. So positive particle, so take out your right hand, okay? Magnetic field out of the page, so your fingers should be pointing back at your face. And if your thumb is towards the top of the page where they are all coming out of, then you will notice that it gets curved like this. Now I'm going to draw it pretty big. Why? Because the alpha particle has the biggest mass. And as we know, the radius gets bigger as the mass gets bigger. It's harder to accelerate it into a circle. Okay, beta positive. Let's stick with our right hand while we can. So it's going to curve the same way because it's positive, so it's right hand. What's different? It's much, much smaller mass. Yes, the charge is a little bit smaller, so that would work to make the radius a tiny bit bigger, but the mass is so much smaller that that'll get completely washed out and we'll end up with a very small radius. Okay, beta negative. Same mass, same charge, just the negative version. So take out your left hand, go ahead and do that. So take out your left hand, thumb towards the top of the page, fingers back at your face, and your fingers should curve like that, and it should have about the same radius as the positive, just other direction. Now the gamma, what does the gamma do? Well, it doesn't have a charge, so how is it affected? So if Q is 0, the radius is infinity, and if the radius is infinity, that's the radius of a circle that is actually not a circle, it's a straight line, which of course just is because it's not affected by a magnetic field. Okay, same thing over here. So now remember, okay, the more it accelerates, the faster it will zoop into one of the plates. So let's start with our alpha particle. It's got the biggest mass, will be hardest to accelerate, so it will actually make it pretty far before it gets sucked in, right? But it'll get sucked into the negative plate. Beta positive, much, much smaller mass, so a much, much bigger acceleration, but the same direction because it's positive, okay? Beta negative will go the other way, but the exact same shape as the beta positive because it has the same mass, same charge, just other direction. And a gamma is not charged, so it will continue on unaffected. Okay, so just a quick note on will stuff decay and when does it stop? So anything larger than Z is always radioactive, meaning no matter the isotope, it decays spontaneously. Okay? However, if Z is less than 82, only certain isotopes will decay spontaneously. Again, it has to do with the ratio of protons to neutrons and the interaction between the strong nuclear force and the electrostatic force. Question here, if radiation is natural and most things are unstable, why are radioactive substances relatively rare? Well, first of all, just because most elements are radioactive doesn't mean that all elements are evenly distributed, right? I think it's like 90% of all matter in the universe is hydrogen. Okay. Second of all, if there was stuff here that was radioactive, it's been around for a few billion years and a lot of it has decayed into more stable stuff. Not much left here on Earth. Okay. Some is being created out in the cores of stars somewhere, but here on Earth, a lot of it's gone now. Okay. All right. So once that decay happens, there's no guarantee that the daughter won't be unstable and then it will itself undergo decay. This continues until all products are stable in what is called a decay series. So just a quick example of a decay series. Okay. We have astatine 215, which undergoes alpha decay, then beta negative decay, and then alpha decay before coming stable. Just wants us to write out the series of reactions. So first it undergoes alpha decay. Conservation of nucleons, I have 4 here. I need to have 215 total. I have 2 positive charges here. I have 33 positive charges before, so here I need to have 31, which makes this gallium. Okay, and then this is unstable. Gallium is unstable. So what does it do about it? It does a beta negative decay. Don't forget the antineutrino. Okay, 0 and 211, so that hasn't changed. 31 and minus 1, so this thing must have 32 positive charges to work out for conservation of charge. So it becomes germanium. But then, as we know, that undergoes decay because it undergoes another alpha decay, right? So once again, this becomes the new reactant. 211 before, so that must have had 207 and 2 positive charges, but before we had 32. So it ends up finally as a stable isotope of zinc. Okay, that wraps up topic 2. You can check the Google Classroom or the agenda for the topic 2 practice stuff if you're looking for practice with this.